Hello everyone. So, till now we have considered flow over flat plate with constant or variable temperature boundary condition. In those cases pressure gradient was 0, right, dP by dx is 0 for flow over flat plate because your free stream velocity u infinity was constant. Today we will consider boundary layer flow over a wedge where u infinity is function of x. So, for potential flow you know outside the boundary layer velocity will vary as c x to the power m, where m is wedge parameter. So, let us consider laminar boundary layer flow over a wedge. This is the case. So, you can see this is the wedge with the wedge angle pi beta and your free stream temperature is T infinity and free stream velocity is u infinity. X is measured along the surface and y is normal to this surface. So, obviously you can see when fluid will flow over this wedge, okay, it will be accelerating, the fluid velocity will accelerate. So, obviously u infinity will be function of x. So, these are the assumptions we will consider: symmetrical flow over a wedge of angle pi beta, uniform surface temperature. So, we will consider Tw as wall temperature as constant, uniform upstream velocity, pressure and temperature, and both pressure and velocity outside the viscous boundary layer vary with distance x along wedge. Okay. So, potential flow theory gives the solution for the free stream velocity as u infinity is equal to c x to the power m, where m is the wedge parameter and c is constant. The relation between these wedge parameter m and wedge angle beta is given here. So, you can see wedge parameter m you can write as beta divided by 2 minus beta, and wedge angle you can write in terms of the wedge parameter m, beta is equal to 2m by m plus 1. Now, you can see that as a special case, if you put beta is equal to 0, m will become 0, and what will be the flow situation if beta becomes 0? So, it will be flow over flat plate. So, you see if this wedge angle beta, if you put 0, then obviously it will become flow over flat plate, and if beta is 0, that means m will be 0, and if m is 0, so u infinity will be constant. Okay. So, it will be a Blasius flow over a flat plate, and if beta is equal to 1, so that will means it will become pi. So, it will be a vertical plate. Okay. So, if flow occurs, then it is known as stagnation flow, and for beta is equal to 1, m will be 1, and if you put m is equal to 1 here, you can see u infinity will be c into x. So, it is a stagnation flow. So, here you can see two different situations for beta greater than 0. Okay. So, in this case you can consider that flow over a wedge with angle pi beta and beta varies between 0 and 1, then the flow accelerates along the surface and pressure gradient is favorable, okay, because dP by dx is less than 0. So, pressure gradient will be favorable and flow will accelerate. For beta less than 0, so if you consider flow through an expansion with angle minus pi beta. Okay. So, beta will vary between minus 1 and 0. So, you can consider this expansion. So, it is kind of diffuser. So, fluid is entering with velocity u infinity. Once it comes here, so you can see it is kind of diverging. So, the wall temperature is Tw and x is measured along this wedge surface, and in this particular case you can see the flow decelerates along the surface and pressure gradient is adverse, that means dP by dx will be greater than 0. And in this situation it may happen that there will be a flow separation, and if flow separates, boundary layer flow theory will not be valid. Okay. So, we will see that at which wedge angle beta flow separates, and how do you know that flow separation has happened, when you will see the shear stress tau w or the velocity gradient will become 0. So, that time you will know that the at that point, okay, flow separates. So, after that boundary layer flow theory will not be valid. So, let us consider laminar boundary layer flow over a wedge, and we will use the similarity transformation technique similar to what we have done for solving the boundary layer equation for a flow over flat plate. We will use that similarity variable as well as the velocity distribution. So, you can see what we derived in similarity transformation approach. Similarity transformation. So, we have used the similarity variable eta as y into g, and g is function of x, and g we have found as root u infinity by nu x. Okay. So, you can see from earlier lecture that we have derived g, which is function of x, is equal to root u infinity by nu x. So, you can write eta is equal to y into root u infinity by nu x. Okay. And what is u infinity? U infinity is your free stream velocity, and we have considered it as c into x to the power m, okay, where m is the wedge parameter. So, here if you put c x to the power m, then what you will get eta? Eta you will get as y into c x to the power m divided by nu x, and you can write as y into root c by nu into x to the power m minus 1 by 2. Now, let us take the derivative of eta with respect to y as well as x. So, what you will get? Del eta by del y you can find as root c by nu x to the power m minus 1 by 2, and del eta by del x, okay, it will be y root c by nu m minus 1 by 2 and x to the power. So, m minus 1 by 2 minus 1. So, it will be m minus 3 divided by 2. So, now let us write down the expression for f prime, okay, whatever we have derived in earlier lecture. So, we have also shown capital F as df by d eta, right, is equal to g by u infinity into d psi by d eta. Okay. So, where psi is the stream function, and we have already told that f is having the physical significance of stream function. Okay. So, from here you can write f is equal to g by u infinity into psi equivalent to that, and you can write psi as u infinity into f into 1 by g. And what is g? G is root u infinity by nu x. So, you can write u infinity f nu x by u infinity. So, from here you can write psi is equal to root u infinity nu x into f, and u infinity is c x to the power m. So, if you put it here, so you will get psi is equal to root c nu into x to the power, you see x to the power half and there x to the power m. So, it will be m plus 1 by 2 into f. Okay. So, you can see psi is function of x and eta, because f is function of eta, we know, right, and also you can see psi is function of x. So, it will be function of x and eta. So, now let us write the von Mises transformation. Okay. So, what is von Mises transformation? So, if from any book you can see this von Mises transformation, if x y is equal to function of x eta, the von Mises transformation you can write as del of del x, okay, keeping y constant, is equal to del of del x keeping eta constant, del x by del x keeping y constant, plus del of del eta keeping x constant, del eta by del x keeping y constant. So, this you can write as del of del x plus del of del eta and del eta by del x. Okay. Similarly, you can write del of del y as del of del eta by del y plus del of del x by del y. So, you can see in this case now you are keeping x constant and you are trying to find del x by del y. So, obviously, it will become 0. So, it will be equal to del of del eta by del y x. Okay. So, from here now psi we have written as root c nu x to the power m plus 1 by 2 f. Okay. So, from here you can write del psi by del x as you can see from here root c nu m plus 1 by 2 x to the power. So, m plus 1 by 2 minus 1. So, it will become m minus 1 by 2 f plus root c nu x to the power m plus 1 by 2 and it will be del f by del eta into del eta by del x. So, what you will get? So, you will get from here. So, it will be f prime, okay, and what is del eta by del x? We have already found. So, it will be y root c by nu m minus 1 by 2 and x to the power m minus 3 by 2. Okay. Similarly, del psi by del y you can find as root c nu x to the power m plus 1 by 2. Okay. So, it will be del f by del eta. So, it will be f prime and it will be del eta by del y, right. So, it will be root c by nu x to the power m minus 1 by 2. Okay. So, what you can write from here? So, you can see it will be c and here it will be x to the power m f prime, okay, and c x to the power m is nothing but u infinity into f prime. So, now let us write the governing equations for flow over wedge. So, we will have the assumptions steady laminar flow. So, obviously, you can write the momentum equation as u del u by del x plus v del u by del y. Now, in this case you will have pressure gradient. So, it will be minus 1 by rho, okay, dp by dx plus nu del 2 u by del y square. So, this is your x momentum equation. And what is the energy equation? Energy equation will remain same, neglecting the viscous dissipation. You can write u del T by del x plus v del T by del y is equal to alpha del 2 T by del y square. So, these are boundary layer equations, right. So, in this case, as pressure gradient is not 0. So, we have written minus 1 by rho dp by dx. Now, we have found the stream function and its gradient with respect to x and y. So, you will be able to find the value of u, v and its gradient. So, first let us write u. So, u is equal to del psi by del y. Okay. So, already we have found it. So, it will be just c x to the power m a prime, and it is same as whatever we have written for the Blasius solution. Okay. So, for flow over flat plate we have already defined a prime as u by u infinity. So, from here you can write the x direction velocity u as u infinity a prime. Okay. And for m is equal to 0, obviously flow over flat plate, okay, u infinity is constant and u is equal to u infinity a prime we have already shown. Now, the velocity v you can write as minus del psi by del x, okay, and that we have found already. So, if you see, it will be minus root c nu m plus 1 by 2 x to the power m minus 1 by 2 into f plus c m minus 1 by 2 y x to the power m minus 1 f prime. Okay. So, you can see from the previous expression from here, okay, so that we have rearranged and we have written in this form. Okay. So, if you rearrange it, you can see you can write v is equal to, you take common as u infinity nu by x m plus 1 by 2. Okay. We have written such a way that u infinity is c x to the power m. So, here m by 2 if you take inside, so it will be c x to the power m, and x to the power minus half will go in the denominator. So, you will get this term as u infinity nu by x and m plus 1 by 2. So, you are left with minus f, and here if you take same c x to the power m by x, okay, so you will get here minus m minus 1 divided by m plus 1 and eta, because you will get y into root u infinity by nu x. Okay. Eta is y root u infinity by nu x. So, if you take common here, you will left with eta into f prime, and if you see this is the similar expression, this in the inside the bracket. Okay. So, if you put m is equal to 0, m is equal to 0, then what will be v? So, v will be m is equal to 0. So, it will be root u infinity nu by x half minus f plus eta, sorry, here it will be m is equal to 0. So, minus minus plus, so eta f prime. Okay. So, this is the expression already we have seen for flow over flat plate. Now, u v we have found. Now, let us find del u by del x and del u by del y. Okay. So, you can see from here u we have written c x to the power m f prime. So, del u by del x you can write c m x to the power m minus 1 f prime. Again we are using the von Mises transformation. Okay. You refer in last slide and use that expression y root c by nu m minus 1 by 2 x to the power m minus 3 by 2. Okay. So, del u by del x expression you can write as, now again c x to the power m we will write as u infinity. Okay. So, it will be m u infinity divided by x, okay, f prime plus u infinity by x f double prime eta m minus 1 by 2, okay, and del u by del y. Okay. So, it will be just c x to the power m f prime root c by nu x to the power m minus 1 by 2 is equal to u infinity root u infinity by nu x into f, sorry, here it will be f double prime, because your f prime was there, sorry, this f prime is there. So, it will be f double prime, and del 2 u by del y square, similarly you can write it as u infinity root u infinity by nu x f triple prime root c by nu x to the power m minus 1 by 2, and that you can write as u infinity by nu x into f triple prime. Now, you see we have written the expression for u del u by del x, v del u by del y, del 2 u by del y square. Now, we need to find the pressure gradient. Okay. So, for pressure gradient, so you can see for boundary layer flow del p by del y is equal to 0, right. So, whatever pressure will be there outside the boundary layer, that will be impressed inside the boundary layer. Okay. So, outside you can use Bernoulli's equation and find what is the temperature gradient. So, you can see the flow outside the boundary layer can be considered as inviscid So, from Bernoulli's equation, you can write P infinity plus rho u infinity square by 2 is equal to constant, or you can write dP infinity by dx, okay, is equal to minus rho u infinity du infinity by dx. Okay. So, you can write 1 by rho dP by dx. Okay. So, inside the boundary layer whatever pressure gradient will be there, that will be equal to the outside pressure gradient. So, that will be 1 by rho dP infinity by dx will be minus, sorry, it will be rho infinity, because you are taking. So, dP infinity by dx, so it will be minus rho infinity du infinity by dx, and by 2 is there. So, those that 2 will cancel out. So, it will be minus u infinity du infinity by dx. Okay. And we know u infinity is C x to the power m. Okay. So, du infinity by dx will be C into m x to the power m minus 1. So, from here you can see 1 by rho dP by dx you can write as minus m, okay, C x to the power m will be u infinity and 1 u infinity is there. So, it will be u infinity square divided by x. Okay. So, now the expressions for u, v, del u by del x, del u by del y, del 2 t by del y square and dP by dx you put in the x momentum equation. Okay. We have x momentum equation u del u by del x plus v del u by del y is equal to minus 1 by rho dP by dx plus nu del to u by del y square. So, all these expression you put in this x momentum equation. So, you will get u infinity f prime, that is your u, del u by del x, if you see it will be m u infinity by x f prime plus u infinity by x f double prime eta m minus 1 by 2 plus root u infinity nu by x m plus 1 by 2. So, we are writing the value of v. Okay. So, it will be minus f minus m minus 1 by m plus 1 eta f prime, okay, and del u by del y will be u infinity by nu x f double prime. Okay. Then we have minus rho 1 by rho dp by dx, you can write as m u infinity square by x, okay, and del to u by del y square. So, you can write nu u infinity square by nu x f triple prime. Okay. So, this is the expression, you simplify it, okay, multiply both side by x by u infinity square. So, multiply both side with x by u infinity square and simplify it. Okay. So, if you do it, you will get m f prime square plus m minus 1 by 2 eta f f double prime f prime f double prime minus m plus 1 by 2 f f double prime minus m minus 1 by 2 eta f prime f double prime is equal to m plus nu will get cancelled, okay, and you are multiplying with x by u infinity square. So, you will get only f triple prime. Okay. So, you can see here these terms will get cancelled, this term and this term, and you will get f triple prime. Okay. This if you take in the right hand side, then you will get m plus 1 by 2 f f double prime plus m if you take common, then 1 minus f prime square is equal to 0. Okay. So, you can see we started with partial differential equation, then after using the similarity transformation we could transfer the PD to ordinary differential equation. So, this equation is known as Faulkner-Scan equation. So, this equation is known as Faulkner-Scan equation. Okay. So, you can see this is a third order ODE and nonlinear, third order nonlinear ODE. Okay. And what are the boundary conditions? Boundary conditions you have, okay, at eta is equal to 0, okay, from u is equal to 0 you can write f prime 0 is 0, and from v is equal to 0 you have the expression of v. So, from there you can write f 0 is 0. It is kind of a stream function where you are assuming the value of stream function on the wall as 0, and at eta tends to infinity. Okay. So, u is equal to u infinity. So, from here you can write f prime infinity as 1. If you put m is equal to 0, then you will get flow over flat plate and you will get the Blasius equation back. So, you let us see whether we get it or not. So, if m is equal to 0, then you can see from this equation m is equal to 0. So, this is the last term will become 0 and here it will be half. So, it will be f triple prime plus half f f double prime is equal to 0, which is your Blasius equation. Now, we have solved for the velocity profile, because this third order nonlinear ordinary differential equation, if you solve using numerical technique, then you will get the velocity profile for flow over a wedge. Now, let us consider energy equation. As a special case, we will consider surface or the wall as a uniform temperature. So, temperature will remain constant. With that assumption, let us find what will be the equation to find the temperature distribution. So, if you see, we have written the energy equation as U del T by del x plus V del T by del y is equal to alpha, which is your thermal diffusivity, del 2 T by del y square. Okay. So, now already we have the transformation details. Okay. Here we are assuming T w is equal to constant, okay, and we are assuming theta is function of eta only, and it is T minus T w and divided by T infinity minus T w. So, from here you can see T is equal to T w plus T infinity minus T w into theta. Okay. So, the equation you can see, you can write, if you put here, so you will get U del theta by del x plus V del theta by del y is equal to alpha del 2 theta by del y square, and theta is function of eta only, and we have the transformation variable eta, right. Eta is equal to y into root u infinity by nu x. So, let us find the value of del t by del x, del t by del y and del 2 t by del y square, and already we have the value for u and v. So, del theta by del x, now you find, okay. So, eta is your y root u infinity by nu x, okay, and del eta by del y you have root c by nu x to the power m minus 1 by 2, and del eta by del x you have y root c by nu m minus 1 by 2 x to the power m minus 3 by 2. Okay. And again we will use the von Mises transformation, and we will find del theta by del x. In this particular case, theta is function of eta only, so easily you can find the derivative. So, you can write theta prime, then del eta by del x. So, del eta by del x is this one, y root c by nu m minus 1 by 2 x to the power m minus 3 by 2. So, this you can write as m minus 1 by 2 x eta theta prime, and del theta by del y, if you write, it will be theta prime, again del eta by del y. So, it will be c by nu x to the power m minus 1 by 2. So, you can write root u infinity by nu x theta prime, and del 2 theta by del y square, it will be just u infinity by nu x theta prime. So, if you now substitute these with the value of u v here, so what you will get, u infinity f prime m minus 1 by 2 x eta theta prime plus root u infinity nu by x m plus 1 by 2, this is the value of v, m minus 1 by m plus 1 eta f prime root u infinity by nu x theta prime is equal to alpha u infinity by nu x theta double prime, multiply both side with x by u infinity and rearrange it. Okay. So, you will get as m minus 1 by 2 eta f prime theta prime minus m plus 1 by 2 f theta prime minus m minus 1 by 2 f prime theta prime is equal to alpha by nu. Alpha by nu, that means it will be 1 by Prandtl number, okay, theta double prime. So, this term will get cancelled. So, you will get finally theta double prime plus Prandtl number by 2 m plus 1 f theta prime is equal to 0. Okay. So, you can see this is the OD and this is linear equation, because already you know the value of f, right, from the velocity distribution. Okay. So, this is known. So, from the Falconer-Scan solution you will be knowing the velocity profile. So, from there you can calculate the f, and if you put for m is equal to 0 as a special case flow over flat plate, then you can see m is equal to 0, that means it will be theta double prime plus Prandtl number by 2 f theta prime is equal to 0. This is your Paulhaussen equation we have already derived for flow over flat plate. Okay. And what are the boundary conditions? So, boundary conditions at eta is equal to 0, t is Tw. Okay. So, if it is t is equal to Tw, then theta is 0, and at eta tends to infinity. So, t will be t infinity. So, it will be 1. Okay. And you can see this is the second order ODE. Using some numerical technique you can solve this equation, you can find the temperature distribution, and if you know that already we have derived the expression for temperature, non-dimensional temperature for flow over flat plate. Similarly, you can do the analysis here and you can find the temperature distribution as non-dimensional temperature, okay, theta you can write as 1 minus eta to infinity e to the power minus m plus 1 by 2 into Prandtl number 0 to eta f d eta d eta, right. So, for Blasius solution you can see m plus 1 by 2, this m is, if you put 0 then it will get Prandtl number by 2. So, this was the expression, and divided by 0 to infinity e to the power minus m plus 1 by 2 Prandtl number 0 to eta f d eta d eta. Okay. And if you remember, we have written the expression for d theta by d eta, it is required to find the Nusselt number or heat transfer coefficient. So, that at eta is equal to 0, right, d theta by d eta at eta is equal to 0, it will be 1 by 0 to infinity e to the power minus m plus 1 by 2 Prandtl number 0 to eta f d eta d eta. Okay. So, once you know the f from the velocity distribution, you will be able to find what is d theta by d eta, and using some numerical technique you can find the value. So, if you solve this Falconer-Scan equation, whatever we have derived, so you will get the velocity profile, and once you know the velocity profile from the energy equation, whatever we have derived ordinary differential equation, you will be able to find the temperature distribution, and once you know the temperature distribution, you will be able to find d theta by d eta at eta is equal to 0, that means the temperature gradient at the wall, and you will be able to find the local heat transfer coefficient, local Nusselt number, average heat transfer coefficient and average Nusselt number. So, if you see laminar wedge flow, so for different beta and corresponding m value is shown here, and if you see Cfx Rex to the power half divided by 2, this value if you see here, then you can see for beta is equal to 0, m is equal to 0. Okay. So, what is your f double prime 0, that means your velocity gradient at the wall. So, that is 0.33206. So, that you have already found, right. So, this is the flat plate case. Okay. And if you see the case where this is your f double prime 0, okay, that means your velocity gradient at the wall. So, velocity gradient at the wall becomes 0. What does it mean? Shear stress is 0, and if it becomes shear stress as 0, then obviously the fluid particle will just float, okay, and that is the point of flow separation, and flow separation occurs at that point. So, corresponding beta value you can see and m value you can see where flow separates. Okay. So, after that your boundary layer theory is not valid, because the important assumptions, one of the important assumptions we have taken while deriving the boundary layer equation is that flow does not separate. Okay. So, here flow is separating at this beta value. So, this is the separation point. Now, for different beta value, so this is the similar case, okay, and at this point you can see that if double prime 0 becomes 0 for this particular beta, and if you see the f prime versus eta, what is f prime? F prime is your u by u infinity, okay. So, u by infinity and eta. So, you can see what is the velocity profile at different value of beta, okay. So, this is the case, okay, where flow separates, and if you plot the f double prime versus eta, then you will be able to see. So, for this particular case where flow separates, you can see the value of f double prime is 0, okay. And rest other beta values you can see you have a positive value, that means shear stress is present at the wall, but at beta value of minus 0.19884 your velocity gradient becomes 0 and flow separates. Now, if you see the d theta by d eta at eta is equal to 0, that means Nusselt number x divided by r x to the power half. So, for different values of m and this for different Prandtl number 0.7, 0.8, 15 and 10, these are the values of d theta by d eta at eta is equal to 0 at different m. Okay. So, now once you know the value of d theta by d eta, you will be able to calculate the local heat transfer coefficient, because k by x root r e x d theta by d eta. So, for at any Prandtl number and any m value, you will be able to find local heat transfer coefficient, local Nusselt number, average heat transfer coefficient and average Nusselt number. Okay. From this table you can see. So, this from the solution of the Falk-Nusskian equation and the energy equation, the value of d theta by d eta is equal to 0 at eta is equal to 0, it is tabulated. Now, let us define displacement thickness, momentum thickness and shape factor for boundary layer flow. So, first let us discuss displacement thickness. Consider just free stream velocity u infinity. Okay. So, if you consider this case, then obviously you can see your streamline will be all parallel to each other, right. So, if you consider a streamline, so it will be parallel to each other, all streamline. Okay. Now, if you bring on flat plate here, so what will happen? So, due to the presence of flat plate, there will be formation of boundary layer, okay, over this flat plate. So, it will okay. So, this is the boundary layer. So, this at this location, this is your boundary layer thickness delta. Now, you can see that in the presence of flat plate, this streamline will be no longer flat, okay, because it will deflect. Why? Because velocity gradient will be there, and due to the velocity gradient to have the same mass flux at each location, this streamline will deflect. So, your new streamline will be like this. So, it was earlier flat straight line, but there will be deflection due to the presence of this flat plate. Okay. Because you can see at this location and 1 and at this location 2, you should have same mass flow rate, and as it is a streamline, there will be no flow across the streamline. So, mass flow rate at 1 should be equal to mass flow rate 2, and hence as velocity gradient will be there, this streamline will deflect, and this deflection is known as displacement thickness delta star. Okay. So, now let us find what is the delta star. So, from here you can see that at section 1 what is mass flow rate will be equal to mass flow rate at section 2. So, at section 1 it will be just rho u infinity into delta, because here also it is same thickness delta. Okay. And at section 2 there will be velocity variation here. Okay. So, it will be rho 0 to delta u dy, okay, plus the mass flow rate whatever is happening here. So, it will be free stream velocity u infinity. So, it will be rho u infinity delta star. Now, divide both side by rho u infinity and rearrange. So, you can find delta star as you can see here, it will be delta minus 0 to delta u by u infinity is constant flow over flat plate. So, dy. Now, this delta we can write as integral 0 to delta dy. So, delta star if you put it here, and you can write 0 to delta 1 minus u by u infinity dy. So, this is the mathematical expression of displacement thickness, and also you can define in this way. Say you have a boundary layer and this is the velocity distribution, and if you have a free stream velocity, then how much distance you have to shift this wall, okay, to maintain the same mass flux. Okay. So, that distance is known as also delta star. So, you can see here displacement thickness delta star is defined as the distance by which the external potential flow is displaced outwards as a consequence of decrease in velocity in the boundary layer. Now, we will talk about the momentum thickness. So, momentum thickness theta is defined as the loss of momentum in the boundary layer as compared with that of potential flow. So, let us consider the same figure here. So, this is your flat plate and this is your streamline, and there will be formation of boundary layer, and this is your delta, this is also delta section 1 and this is your section 2, but there is a deflection in the boundary layer, and so this will be your delta star, right. This is your displacement thickness. So, you can see that if you see the rate of momentum at section 1 and section 2, it will not be same, although mass flow rates are same. So, there will be deficit in momentum at section 2. So, this deficit is known as momentum thickness. So, mathematically if you see here, so what is the rate of momentum transfer at section 1? At section 1, okay. So, what is that? That will be your rho u infinity delta, that is your mass flow rate, and into u infinity. So, that is your momentum. So, rho u infinity delta into u infinity. Okay. So, that will be rho u infinity square delta, and rate of momentum transfer at section 2. Okay. So, at section 2 you can see, so it will be rho 0 to delta u and again u. So, it will be u square dy. So, this is your momentum transfer in this section, and in outside it will be plus rho into u infinity square delta star. Okay. So, now you see there will be a deficit, and this deficit, momentum deficit, you can find the momentum deficit. Okay. So, this the difference you can write as rho u infinity square into theta, where theta is the momentum thickness, equal to rho u infinity square into delta minus rho 0 to delta u square dy minus, okay, rho u infinity square delta star. Okay. And you know the value of delta star we have found in last slide. So, it is 0 to delta 1 minus u by u infinity into dy. So, you put this value in the delta star, you divide by rho infinity square, rearrange this, you will get theta as 0 to delta 1 minus u by u infinity into dy. Okay. And shape factor. So, a shape factor H is used in boundary layer flow to determine the nature of the flow. So, H is defined as ratio of displacement thickness to the momentum thickness. So, H is equal to delta star by theta, and you can see it is known as shape factor because it solely depends on the shape of the velocity. Okay. So, the higher the value of H, the stronger the adverse pressure gradient, and large values of H implies that boundary layer separation is about to occur, and for Blasius laminar boundary layer flow you can find H is equal to 2.59. So, in today's class we considered laminar boundary layer flow over a wedge, and we defined the wedge angle and the wedge parameter, and velocity varies as Cx to the power m as a potential flow, and then we defined the stream function and the similarity variable eta, and from there we found the velocity u and v from the stream function gradient. And later we from the momentum equation we substituted this value of u, v and velocity gradients, and we derived the Falconer-Scan equation, and you can see the Falconer-Scan equation is the third order nonlinear ordinary differential equation. So, using any numerical technique you can solve this ordinary differential equation. Then we considered energy equation keeping the Tw as constant, and again we defined the non-dimensional temperature theta, which is function of eta only, and we converted this partial differential equation to ordinary differential equation using similarity transformation, and that is second order ODE and linear, and from there we express the non-dimensional temperature and also d theta by d eta at eta is equal to 0. Then we have shown the numerical solution for this Falconer-Scan equation, and we have shown that flow separates at a particular value of beta, and after that your laminar boundary layer theory will not be valid. At last we defined the displacement thickness as well as the momentum thickness and shape factor. Thank you.